Muted it.
Good evening. Welcome to tonight's Discovery Lecture Series here in the Marston Theater with the School of Earth and Space Exploration. Thank you to all our VIPs and all our other guests that are here. My name is Scott Smaz. I'm a program manager with the ASU New Space that some of the slides you had saw earlier, talking about our engagement with commercial space enterprises such as SpaceX and Virgin Galactic, and bringing them into the fold of CC, Fulton, and a bunch of other schools here across campus. Tonight's lecture is Laurence Garvie. He's the research professor and curator for the Center of Meteorite Studies and associate editor for American Mineralogists. He's earned his PhD at the University of Bristol. And fun fact, he's worked here 22 years at the Arizona State University. His research focused primarily on carbonaceous chondrite meteorites. Karin from CC wanted me to say curvaceous chondrite meteorites, but reading the script. He provides a unique record of the physical and chemical processes that shaped our solar system. He deciphers early solar system processes through the use of innovative high spatial resolution electron, microscopic, and spectroscopic studies of meteorites. This talk will explore the history of meteorites, how often they impact Earth, and the local and global threat of asteroids. Laurence?
Okay, thank you, Scott. Thank you, everyone, and welcome here, and thank you for coming to this new Discovery Lecture series, where I'm going to be talking about meteorites, asteroids, and what happens when they hit us here on Earth. But first, what I'd like to do is to set the scene for this talk. I've got a small video that I'd like to play. And I don't know how many of you have seen this video. Has anyone seen this? This is, what we've got to do is set the scene here. This is, I've got to turn this down a little bit. This is 15th of February, almost exactly 2 years ago now, 3 years ago now, 9:22 in the morning. Somebody's standing on the balcony in southern Russia. A massive bolide, massive fireball has just passed overhead. So probably about a minute or two before they're filming this. So they're just standing there. They're not knowing that something's about to happen. How many of you know what's about to happen? Okay, I do sort of warn you. So this person did not know that even though the visual spectacle that just happened, that coming towards them at the speed of sound was this blast wave, this shock wave from this bolide that had just passed overhead. And what you're hearing is the multiple booming, the multiple banging of the individual, once this thing broke up, the individual meteors that are going faster than the speed of sound, all deaccelerating. So this goes on for several minutes. So this is just sort of setting the scene. It was really this event 3 years ago that really sort of opened the public's eye to dangers and impacts from space. So this was just sort of to start the show. So really what we're going to do is, first I'm going to start the talk with a few definitions, just so that we all know what we're talking about. Then we're going to look at examples of impacts by size, from dust-sized grains, the most numerous impacts onto the Earth's atmosphere, up to the really big one, the one that happened about 66 million years ago. And then a few slides on impact frequency, when can we expect the next really big impact, and then a few closing remarks. So the point that I really want to make here, that I want people to understand, that people often get this idea of meteorites and meteors interchangeably mixed up. A meteor is something you just see. It's that spectacle you see in the sky, that bright light in the sky. Whereas the meteorite is a thing you can actually touch, not necessarily pick it up if it's too heavy, but something you can actually come up to and touch and study in the lab. So that's meteorites, you can touch them. Meteors, you can just see. Whereas a bolide here is a really big meteor. That's something that's really visually stunning. And lots of maybe people have reported it in the news or something like that. But it's a super bright fireball, and probably most people have seen one or two in their lifetime. And then those things that impact on the Earth, there's meteoroid, relatively large, meter-sized. We're quite happy when those happen because we get to go out and collect them and study them in the lab. And asteroids, we don't want too many of those hitting us. So where did most of these things come from? Here's sort of a schematic up here on the top left. Here's our little orbit for Earth right here. Then there's Mars. And between Mars and Jupiter, we have the asteroid belt. This is where the vast majority of the things that fall onto Earth come from, that we pick up as meteorites. There's millions and millions of objects out here. But unlike what you've probably seen in some recent science fiction movies, this is not an area that's just bustling with large stones that are all banging into each other. There are several movies where that come to mind where we've seen that. This is actually an area, you can imagine sort of like a donut-shaped area around between Mars and Jupiter, where, okay, there's millions and millions of stones, but they're very far apart. So a spacecraft could easily fly between Mars and Jupiter and never actually hit an asteroid. Yet there's still millions and millions of rocks in this region of space. And what's also interesting, the fact, even though we think of this vast mass of material in the asteroid belt, what's actually out there is only about 4% of the mass of the moon, if you got it all together and put it together as one mass. So it's actually not a very large amount of material. And here are some examples that we have here. These are what I'll be showing is primarily things that we have in our collection up here in the Center for Meteorite Studies in the Meteorite Vault. The top right here, you can see here, this is a small fragment of a really rare meteorite that fell in 1961 in Texas called a carbonaceous chondrite. There's been a huge amount of research been done on this type of material because it contains some of the most primordial organic materials that were formed in the early solar system that were then delivered to Earth. On the bottom right, about the size of a small orange, is the latest fall that we have here in Arizona called Whetstone Mountains. And this is just this beautiful oriented stone. It's a stony meteorite. And the bottom left is actually one of my favorite ones. This is called El Mirage. This was actually found here in the valley in the early 70s by a 9-year-old boy who was out biking, was out just biking in the desert. It's now an area that's built up. And this boy actually brought this stone to Carlton Moore, who's our founding director. And Carlton acquired this stone. It's one of my favorite pieces in the collection. This is a complete stone. There was even some remnant fusion crust on the outside. So a really beautiful and really fresh meteorite. So these are all things that come from the asteroid belt, just a small selection of examples. But we also have meteorites from two other sources. Mars, we now have a nice selection of meteorites from Mars. These are samples, even though we keep sending spacecraft to Mars, and we've been doing this for years now, we've got beautiful information and beautiful photographs from rovers on Mars, we still haven't brought a sample back. Whereas nature has done it for us. Impacts on Mars have ejected materials off the surface, and by chance, some of those materials can intersect with the orbit of Earth and land on Earth. And the most recent Mars rock to land is this one here on the bottom left. This one's called Tissant. This is one that we have upstairs. This landed in 2011 in southern Morocco. And what makes this so special is the fact that it's so pristine. It landed in a desert environment in southern Morocco, and we're now keeping it here. We're now curating it here in really a dry environment. And through study of this particular meteorite, we've been able to answer some very fundamental and very difficult to answer questions about processing on Mars, about the geology on Mars, about hydrogen on Mars, how much hydrogen is there, and where did it come from. On the top right is another Mars meteorite. It's got the not very nice name of NWA 7034, but it's also called Black Beauty. This is a meteorite that was discovered only a few years ago, and it's the first meteorite from Mars that's been found and recognized that actually appears to be sort of a collection of materials from the surface, something we call a regolith breccia. And it's giving us, through study of this particular meteorite, the unique insights into the history and the processing on the surface of Mars. And this one in particular seems to have about several weight % of water or hydrogen in the sample. So continuing studies, we're only just beginning the studies on this particular meteorite. It was only found just a few years ago. On the bottom right is another Martian. This is another Martian meteorite called Lafayette. And this one's particularly interesting because if you look, this is like, okay, this is not the actual meteorite itself as a whole. This is just a thin, thin section through the meteorite. You're looking at the meteorite through a microscope, and you're seeing these red areas, these red patches here between the mineral grains. These are actually clay minerals and iron oxides that formed on Mars. So what does that tell us? That tells us about a history of water processing, of aqueous processing on the surface of Mars. So by looking at these meteorites, we can actually build up a very detailed history about water activity on Mars in the past and probably also at the current time. We also have meteorites at from our nearest neighbor, the Moon. We actually have quite a lot of meteorites in these. When I say we, I mean scientists in general. We have well over 200 meteorites that have now been found and recognized to be from this moon. And they really give us a much more detailed history of the geology of the moon itself. When the astronauts went there, they brought back something along the lines of 400 kilograms of material from a relatively small area that was geochemically not very, it was a very distinct area. What these meteorites are actually doing is giving us ideas and giving us information about the whole surface of the moon in general. And by studying these particular samples, we can gain a much deeper understanding of the geology of the moon. So we have meteorites from the asteroid belt. They tend to be things that are about 4.5 billion years old. They are collections of materials from the early solar system that are telling us about early solar system processing and what materials there were that made up our Earth itself. But then we also have things from Mars and the Moon and tell us about the geology of these two objects, of these two bodies. So things are falling all the time, but then we want to know, well, how many meteorites, where's all these things coming from? How many meteorites could actually fall on the Earth? And for that, we can look at something that's called, we can look at what are called the minor planets discovered. This is an amazing, what's called the Minor Planet Research Center. It's a sort of a central body for collating all of the known asteroids that are out there. And I downloaded this particular page today. This is being updated daily. So if you look here, today, as of today, this month, we have 7,000, just this month by itself, 7,019 asteroids. New asteroids discovered, their approximate sizes determined, and their trajectories determined. Those are things, most of those are in the asteroid belt. But then there's also a class of objects that we call near-Earth objects. And so far, 136 of those have been discovered just this month. Those are objects that have the potential to impact on Earth. Those are objects that intersect with the Earth's orbit or are very close to the Earth's orbit. So we have on total now of objects that we know of that have the potential to impact with Earth. We have about 13,000, almost 14,000 objects. So this is it. The numbers are increasing every single day. If we were to look tomorrow, there'd probably be another 20 or 30 here. So this is telling us that of asteroids that we know of, and we know their orbits, we have over 700,000. And if we look on the right up here, it gives here what we call close approaches. These that are come within a certain distance to the Earth. And we can look at today, if we look at a few days ago, February 15th, we had LDs called lunar distance, which is a lunar distance is a quarter of a million miles approximately. We had something come quite close to the Earth. It was something that was quite small. It was between 5 and 12 meters in diameter. And just to give an idea of how big 12 meters is, this screen here is about 10 meters in diameter. So that's considered a small object. And if we look for today, what do we have? February 18th, we have, these are actually quite far away, so 36, 24 lunar distances, but again, quite a bit larger. So something like this, if it impacted with the Earth, would be quite a significant spectacle. So there are several NASA-funded organizations that are trying to identify all the known near-Earth objects to understand what dangers they pose to us. So what I'm going to do for the next few slides now is look at known collisions that are happening all the time, from the very, very small to the very large. The vast majority of the material that impacts with the Earth is dust size. Now, I put a number up here of 78,000 tons, and I've seen in the literature, I've seen people quote 40,000 tons, I've seen 100,000 tons, but it's several tens of thousands of tons of material falls onto the Earth every single year. The vast majority of the material that lands on the Earth, though, that hits the Earth's upper atmosphere, is dust size. And I really mean dust size of a dust grain, size of a sand grain. And what happens is this material is hitting the Earth at high velocity. The velocities are between 11 and 78,000 kilometers per second. And I put that into miles per hour. That's up to 175,000 miles per hour at the highest velocities. So what happens is, you can imagine these little dust grains are hitting the upper atmosphere, these super high velocities. They're hitting the air. They're compressing the air in front of them. And when you compress air very rapidly, it heats up. And that heated up air is then heating the sample. It's heating the little dust grain. And it's heating it to such high temperatures that it's instantly vaporizing it. It's instantly making a small meteor. So that's what you typically see when you see a typical meteor in the sky, just that little event. That's something that's dust-sized, moving at 20 or 30 kilometers per second, and only lasts in the atmosphere for a second or two. Whereas something on the order of, let's say, 9 millimeters or about a centimeter would actually would make quite a spectacular meteor. I love this picture. There's a group of people that study what are called micrometeorites. When these small dust grains come into the atmosphere, a significant proportion of them aren't ablated completely, but they're reheated and remelted, some of them, and they rain down slowly onto the surface of the Earth. And there's a group of scientists that actually study these micrometeorites. And this one's actually from John Laurence up in Norway. This is a sphere of glass with a small nickel-rich iron core on top. So we know this is meteoritic from the composition. And this whole piece of glass, this whole object, is only 1/4 of a millimeter in diameter. And it was actually found in a gutter in northern Norway. You can find micrometeorites anywhere. So it's a case of collecting the materials that's landed over time, washing them in water, and looking at them under the microscope. So this particular project is called Project Stardust. They've been collecting and analyzing micrometeorites for many, many years, and they give us more insight into what's out there. The meteorites only represent a small proportion of the types of materials that are out there, but some of these micrometeorites, some of the materials that we call interplanetary dust particles, may be cometary in origin. So there's a large group of people scientists that actually study these materials. If we get larger, so masses, this big, for instance, to a few meters in size, maybe up to a few tons, as these objects come into the atmosphere, they produce a really amazing spectacle. Again, they're compressing the air in front of them, and this compressed air is heating up the sample. We have massive, massive ablation of the material. People often ask, how much material is typically ablated from something that, let's say you pick up an object that's that big, how much was ablated? Probably, we don't know exactly, but probably 50 to 90% of the material is ablated in those few seconds that it passes through the upper atmosphere. And then what happens, if the material breaks up, it then slows down, it loses a lot of that kinetic energy, and then it falls down onto the ground at maybe 200 to 300 miles per hour, let's say 400 to 700 miles per hour, depending on how large the sample is. And at this stage, it's called dark flight. It's not glowing, it's not hot, it just falls down onto the ground. And so if you imagine a stone or a small stone just falling onto the ground at maybe 100, 200 miles an hour, it's literally just going to land there. It's not going to make a dent, or it's not going to embed itself into the ground. And I'd actually like to dispel this myth. If you can see that, I'll read it here just in case you can't see it up here. The myth is meteorites are hot and glowing when they reach the ground. It's quite often, maybe once a month or so, that I'll get somebody from a member of the public phoning me up and say, I found a meteorite, and I always then question them, say, well, what were the circumstances? And at least once a month, somebody tells me it was glowing, or it was hot, or it was so hot that they couldn't touch it for several hours. And I know immediately it wasn't a meteorite. And it's that popular conception. It's one of those things that we see in science fiction movies again, that it was when it lands, it's hot and glowing, you can't get close to it for days. And actually, when I actually looked up just before I came down here, I thought, what are the temperatures in space? So if you're just above the Earth and you have an object that's up there in the direct sun, it may get to about 200 degrees Fahrenheit, so quite hot to the touch, but definitely not glowing hot. But if it's in the dark side, if it's out of the sun, it'll actually get to about minus 200 degrees. It'll actually be so cold it'll be difficult to touch. And we have a few authenticated reports of recent falls where it's gone through somebody's roof and they've gone to pick it up, and they've actually dropped it because it's so cold, not because it's so hot. And by the way, I put this next slide together. I wanted to put a really elaborate slide together, but I really didn't have time, so I just sketched something, and this is the sketch. but I thought, I could spend hours and hours and hours trying to do a special thing in Photoshop and so forth, but I really wanted to just show what's actually happening and the scale and the times that things are happening. The atmosphere, so here we're in space, an object hits the upper atmosphere, going at 20 kilometers per second in 4 seconds. 1, 2, 3, 4. It's already in the stratosphere. It's a bright fireball. And here the pressures for most of the stony meteorites is so high that here it explodes, it breaks apart. And you see that quite often if you look at videos of meteors where there's been collections afterwards, where they've been able to collect stuff. There's a big flash, a big bright flash, where the thing literally disintegrates into small pieces. And at this stage, 20 kilometers, it slows down to a dark flight mode, and it spends the next 3 minutes or so falling onto the ground. So it's quite amazing to think we have 4 seconds over this 70 kilometers here in 4 seconds, and then 3 minutes for this last 20 kilometers just to hit the ground where we can pick up the meteorites. So things happen very rapidly, and this, the scales here, whether it's 4 seconds or we'll see a video in a minute, which is actually about 18 seconds, but that's where something comes in at a very shallow angle. If it comes at a shallow angle, obviously it can have a longer trajectory through the atmosphere if it does break up, before it breaks up, and then things drop in dark flight. And to give an example of of a meteorite that was not hot when it landed, this is the very famous Allende fall from 1969 in northern Mexico, and this is one of the stones. This one's about that big, size of a soccer ball. It fell into a field with lots of grass and hay, and it just stuck to it. It didn't carbonize, it didn't catch on fire. This is an example of things, again, they're not hot, or they're not burning hot when they land. The other thing with meteorites is that the vast majority of meteorites, which are very small. When you look at collections like the collection we have here or in other collections, we tend to show the really large, the really impressive meteorites. But in a sense, they're really the rarity. The vast majority of meteorites, what's called the mode in the statistical terms, is about 1 centimeter or 2. And this is an example of a meteorite that was found by Robert Ward. It's a very famous fall in in Spain in 2007. There's the meteorite. And it's actually a really rare sample. It's called a eucrite. And they spent days and days and days searching for these few small stones. And actually, most of the stones were actually found in olive groves. And that was actually one of the biggest difficulties, distinguishing something like this from a dried olive. But they were able to find about half a dozen stones. But this also indicates why it's so difficult to find meteorites, especially like somewhere here in the southwest, where we have desert varnish-covered pavements. So can you imagine trying to find a black stone on the black desert varnish-covered pavements? Almost impossible. Meteorites fall everywhere. Everywhere around the Earth. So as you imagine, since the Earth is 70% water, most of the meteorites are going to fall in the oceans, for example. A lot of meteorites are going to fall in terrain that's inhospitable, places where we can't find them, like in forests or in grasslands, for instance. And so the places where most of them are found in deserts, both hot and cold deserts. Here's at the top right is Caroline Smith. She's my counterpart at the Natural History Museum in London, in the Nullarbor Plain in Australia. And I think that little black dot that she's got on the knife there, I think that's a meteorite. It was actually difficult to see from the photograph. Bottom right are teams that go to Antarctica in their summer every year and collect meteorites from the snow there, and they come back typically with hundreds or thousands of new samples every year. And the bottom left is one called Chandler, one that I found accidentally a few years ago while hiking just southwest of Chandler. Here was just sitting in the sand here. It's only a part of the stone there. I was not able to find the rest of it. And again, to illustrate the fact that when they hit the ground, they don't make these small stones that are going just a few hundred miles an hour. They don't make a huge dent in the ground. Here's the one found. This is Whetstone Mountains, felled in 2009. It was actually Jack Schrader who found the first 45 hours after the main spectacle, the fireball that was seen, found the first stone. And here's one of the, I'm not sure if this was the first, it might be the first one. And you can see where it impacted there, just made a little dent in the ground. You can use the barrel cactus up here for scale. So this is just something that's about the size of an orange. And you can see as it hit, it broke into 1, 2, there's a third piece up there. So these things don't make a big impact, the vast majority of them. And just to give an indication of these falls are happening all the time, about the last week or so has been very active around the world. We've had a fall about an hour ago somewhere in Texas. I just got a phone call before I came in here. A few weeks ago in Florida. This is the latest, not the most recent collected fall. It was actually even a more recent fall in Denmark just a few days ago. So these things are falling all the time, and the difficulty is finding them. In this particular case, there's the meteorite. There's some, looks like lipchap or something like there. So that's for scale. It's only about 8 grams. And the reason they were able to find this is because of Doppler radar. That they had fantastic Doppler radar coverage in northeastern Florida. So they could actually track the dark flight of the stones after the explosion of the main fireball. And then basically they could go and it still took them 6 days of searching to find the first stone. And once you found the first stone, it's basically X marks the spot. And you can start looking around there, and they found another, over the next few hours, they found another few stones. So this is one that's, we don't even know what type it is yet. It hasn't even been classified. And the provisional name is here. This is just the local town. And what I had meant to say earlier, what I haven't said yet, we actually classify meteorites, or to sort of informally classify meteorites into 2 types, falls and finds. This is a fall. This is the freshest sort of material that we have. This is the type of material that collectors like, and then we also like, because they're the freshest materials. They're least altered or least weathered materials. As we get larger samples, larger and larger samples, I love this bottom right picture. This is actually meteorite, the Hobart iron in Namibia. It's the largest single intact meteorite that we have. And this is Dr. Fernie. I think that I couldn't find the date of this. I'm guessing it was taken sometime in the 40s or 50s, because the photographs of this area now, this thing is built into an amphitheater. And you can see where the soil line is right here. So you can see where the soil line is. So you would imagine that something of this size would have actually made a bit of a crater. And yes, if this had landed in one spot, there would almost certainly be a crater. But there's an interesting story about this sample. When they excavated around and underneath it, there's no evidence that the Earth is compacted underneath. So it doesn't look like the initial impact was actually at this site. And so there's some speculation that it came in at a low angle and bounced on the Earth and landed at this site. Because otherwise, there's no evidence, no compacted soil or anything under this thing. Anyway, this is the largest one that we have, largest single sample that we have. And as you imagine, as you get to larger and larger samples, you know, the fireball is going to be bigger and bigger and bigger. And one of the examples, we're going to go through three examples now. And I'm going to use this 747 as an example. Here's the size in relation to give you a scale. There's the Hobart iron up here, the largest iron found. Now we're going to look first at this one, Carancas. This was this was something that really opened our eyes to sometimes something unexpected can happen. This was the news report, the Reuters news report. Peruvians get sick from apparent meteorite crater. There was a bolide that came in during the day. Hundreds and hundreds of people saw it hit the ground, made a beautiful crater. But what happened was when the object hit the ground and made the crater, we'll see a picture of the crater in a minute, it hit the ground, which almost instantly started filling it with water and started bubbling and producing noxious gases, almost like steam. And so people associated the noxious gases and the steam with the meteorite. They thought it was the meteorite that was producing this gaseous material. Here's a picture of the crater itself. It's about 40 foot in diameter, I think I said, something like 40 foot in diameter. And that was caused by an object that was only about this big when it actually hit. But this one was really unusual. There was something really strange about this sample. When it was caused by a stony meteorite that was very friable, and it defied all expectations, the fact that it survived, retained its a large part of its extraterrestrial velocities, and hit the ground at something on the order of 6 kilometers a second, forming this crater. So there was a lot of speculation. Why didn't this object break up in the upper atmosphere like all the other stony, or a lot of the other stony meteorites do, break up into small pieces and land down on the ground, as normal meteorites do, once they fall down during their dark flight phase. This thing didn't do that. This thing hit the ground as one single mass. In fact, if you look at this is what was collected. Not much more than this was collected. So 3 tons of material hitting the ground, it completely broke apart on the ground. But when you look at the individual samples, you wonder why and how did this stuff stay together? This meteorite is so friable and so soft. And so scientists had to go back and try to figure out what were the conditions that allowed a 1 meter size object to come into the atmosphere and not completely break up in the upper atmosphere. And they modeled it by coming in at a very shallow angle. So instead of coming straight down to the Earth's atmosphere and suddenly almost like hitting a wall of compressed air, it came in at a shallow angle, and the pressure increase on the sample from the air, the pressure increase on the sample from the air was more gradual, and it didn't break apart before hitting the ground. So it really shows us that we don't know everything. You know, this was something that was totally unexpected. We did not expect something so small hit the ground at 6 kilometers a second and make a crater. And actually, it was the first meteorite where we actually have recorded seismic data of the crater, of it hitting the ground and forming the crater. And so this was 47 kilometers away. They had some seismometers. The ground's not shaking. And then the first ground shaking takes place. These are when the object hit the ground, the waves travel through the ground and intersect the seismometer. And then we have the air blast waves also recorded a few seconds later, actually. The next one we're going to talk about is the one that we started with, the Chelyabinsk. It was an object about we estimate around 17 meters in diameter. And I was trying to think how big would that object be. And it's actually probably about the size of this whole room. So imagine something about the size of this room hitting the atmosphere about 20 kilometers per second. That's what that object was. And again, when it comes to asteroids, that's still not a very big object. Okay, I'm going to show 2 short videos here again. Again, these ones aren't loud, so you don't need to worry, but I will turn it down. Look at the top left. There we are, right there. There comes the fire. Now this is in real time. Well, this is a very low-angle trajectory again. Lots and lots of time for this thing to break up and flare up and break into small pieces as it's coming lower and lower and lower into the atmosphere. And I think we've got one more short video. Again, top up there. There it is coming in there. Flares breaking up again, and all along this trajectory. So this is the smoke trail it's leaving, but all along this trajectory, it's basically leaving small stones that are now dropping down onto the ground. They're in dark flight. So they're now slowly dropping down. And the same thing also, now even though we've seen this spectacle, we're seeing it at the speed of light, the sound wave is now coming out at about 300 meters per second from this little line here and intersecting with the ground first and then the surrounding environment. And in the local town of Chelyabinsk, which is quite a large town, several thousand windows, many thousands of windows were broken. Stone walls were blown over. Fortunately, nobody died. Lots of people were injured, though. So this event really made people realize that these things happen. And the fact that we caught this on film, so many people had dash cams, so many people caught this on film, it was immediately in the news all around the world. So how heavy was it? We say about 10,000 tons, and I was trying to think, well, what does 10,000 tons actually mean? For me, it was actually very difficult to visualize what 10,000 tons is. So I tried to make a comparison. I came up with 14. To me, 1,400 elephants actually means something. 10,000 tons doesn't mean a lot. So a lot of mass in this thing, but a lot of mass, yet only less than a ton of material so far has been collected. So most of that material was actually vaporized in the atmosphere as it was coming in. You saw that wonderful smoke trail. So it exploded. The main explosion we saw was about 23 kilometers above the Earth's atmosphere in the stratosphere. Came in at about almost 20 kilometers per second. That shock wave that propagated out was equivalent in energy to 500,000 tons of TNT, so half a megaton of energy. And the shock wave actually was reverberated around the Earth twice. It was detected all around the Earth in the upper atmosphere. So we think of it in human terms as a huge event, but it was actually not a very large event. I was going to show one more video because this one's fantastic. It's not often that you're able to see somebody actually finding a meteorite from a fall. So this is a little bit of sound. They're speaking Russian. I don't speak Russian, so I hope they're not saying anything inappropriate. So down here, this is snow. There's a little hole in the snow. So he's just going to start digging. He's just digging down. He's digging down. Everyone wishes they could do this. This is absolutely fantastic. So there's a little pinnacle. So you imagine the stone went into the ground and formed a little pinnacle where it compressed the snow. There it is. There's the meteorite. That's an amazing find. And so for the first few days after the fall, they had nice fresh snow on the ground. So all they were doing is just walking around and looking for the little holes in the snow, digging down and picking them out. It became a bit more difficult after that because I think it thawed a little bit and it snowed a bit more. And so they weren't able to collect any more materials until the fall and the spring. But because this object came in at a low angle and kept breaking up and breaking up and breaking up, it dropped thousands or tens, maybe even hundreds of thousands of stones onto the ground. And this is just a small selection of some of the materials that we have here in the center. Here's a 1 centimeter scale cube. And can you imagine people just walking around on their hands and knees picking up all these stones, and all the meteorite dealers going to this going to this area and buying all the stones and then basically distributing them all around the world. And it's one of the few meteorites you can go onto like eBay, for instance, and just buy. There's so many for sale. And so everybody can own a meteorite now. But the largest mass that was found was only about, 570 kilograms. This is the largest mass. And just by bad luck, I was going to say fortuitously, but bad luck, this stone landed in the one small lake at the end of the trajectory. I mean, of all the places this thing could have landed and been nice and preserved and so forth for science, it landed in this one small lake. They had to wait for the thaw and go down and retrieve it. So even though it's a wonderful sample to have, it still sat in the lake waters in the mud for many, many months before it was collected. This is the largest piece from that fall. But let's look at something that's more local. We're going to look at an iron meteorite now, and we're going to talk about Meteor Crater or Meteor Crater here in Arizona. And this is something that probably many of you have been to, everyone's heard of. It's the best preserved crater, Meteor Crater anywhere in the world. It's about a kilometer, just over a kilometer in diameter. Here's the visitor center right here. Happened approximately 50,000 years ago. And it was something probably on the order of 50 meters. So again, this screen from this side here all the way over to here is 10 meters. So 50 meters, so 5 of those. So something, again, probably on the order of 500 million tons, traveling at 20 kilometers per second, hitting the Earth, instantaneously forming this large crater, vaporizing a lot of the impact directly on impact, but still dropping a lot of meteorites around the outside. We'll talk a little bit about this. And so a lot of the questions are, meteorites that we pick up in the plains around here, did they come from the main impactor? Or did we have a sort of a closely knit swarm of material coming in and dropping meteorites all around here, but the main body forming the crater here? And I just want to show this picture. I think this is quite amazing. So in 2011, when the Center for Meteorite Studies celebrated its 50th anniversary, We went up there as a large group of people. One group went down into the bottom of the crater, and one group went around the outside of the crater. And you can just see the group in the bottom of the crater just there. You see those little dots there? So I think it really gives you an idea of the scale of this crater, because it's always difficult to tell about scale. So that's the group of people that went down at the bottom of the crater just there. So what most people are familiar with when we talk about Meteor Crater, when we talk about the irons, when we talk about what's collected there, are the iron meteorites. And this is some of the samples that we have here in the collection. These are the few of the irons. We see these what are called thumbprints on the outside. These are called regmaglyphs. These are individual lumps of iron that were probably not directly attached to the main impactor that made the crater, but were probably closely associated with it. So each one had its own independent flight, but was closely associated with the main impactor. And so these were dropped all around the crater, all around the outside of the crater. One of the mysteries that's been sort of still discussed is what happened to all that 500 million tons of material. Where is it all? We probably have an estimated, I think it was something like on the order of 100 tons of irons that have been collected over the years. So where's all the rest of the material? Well, it turns out that a vast amount of the material on impact immediately, I'm going to say vaporized, though it's not quite the correct term, but formed little droplets, which formed a vapor plume around the crater, which then condensed around the crater. So each one of these little spheres here, each one of these little objects, is actually a small piece of nickel-rich iron and iron sulfide. So if you cut one open, it's still nice and shiny inside. So it looks like a vast amount of the material actually formed these what are called impact spherules that are littered around the crater. We also know that the impact itself was violent. Obviously, it formed the crater, but the closely associated pieces that were basically were hit by the outgoing shock wave instantly converted some of the carbon in the materials to little bits of diamond. Here's a little cluster of diamonds here, right there. There's, again, 1 centimeter scale cube. And so we've been studying these diamonds for many years now because they're essentially a natural laboratory for figuring out how carbon can convert directly into diamond. And so I've got a picture here of some of the diamonds that I extracted from one of the meteorites. This is 1 millimeter from here to here. So they're black, but by studying their structures, we've been able to gain a really good insight into the diamond forming process. So by studying these meteorites, we can also ask some very important material science questions as well. So the last example I'm going to pick here is the one that, again, that we've all heard of as the Chicxulub crater. Something about 66 million years ago, an approximately 10-kilometer size object impacted on Earth near what's now the Yucatan Peninsula, forming a 200 to 300 kilometer diameter crater. The timing of this impact is coincidence with an abrupt global ecosystem disruption or change, and also extinction, as we know, of the dinosaurs, is what we commonly hear, of several key animal groups. This impact was so large in comparison to all the others. It had global effects. All the others had regional effects or no regional effect at all. So Meteor Crater 1 would have affected things in sort of that part of Arizona, but it wouldn't have had any sort of effects a few hundred miles away. We've heard it and seen it, but it wouldn't have altered the climate in any way. But something of this size, 10 kilometers, had worldwide effects. They had tsunamis in that area, probably up to a kilometer high or so. Global wildfires from heated ash coming back into the atmosphere, and vast amounts of dust emitted into the atmosphere and affecting the amount of light that gets down onto the Earth. And so it's generally taken as fact that this giant impact was responsible for the demise of the dinosaurs. What I'd like to do first, though, is to look at what was the very end of the Cretaceous. What was it like just before this impact came onto the Earth? It was generally a very warm place. The end of the Cretaceous was a very warm place. Temperatures were about 10 degrees higher on average than today. Sea levels were much, much higher. There may not have been any polar ice at all. If we look at CO2 levels, atmospheric CO2 levels, today we're around 400 parts per million. That's around here. They had values up to 1,400 parts per million just before the impact. So temperatures were very, very warm around the Earth. And there were several iconic species that we all hear of the very end of the Cretaceous. You know, there's been some speculation as to whether the dinosaurs were already slowly in demise, were already dying out. But certain groups of dinosaurs, such as the Triceratops, were very, very active. They were there in large numbers right up to the very end of the Cretaceous. Things like flying reptiles as well. This flying reptile. We've all seen ammonite, anyone who's been fossil hunting in Cretaceous sediments, and belemnites as well, both cephalopods. But the sea also had many other groups of animals that also died out, one of which is called rudists, which are a bivalve. They were so numerous in the shallow seas that they actually made up reefs, and they pushed out what we now see in reefs as corals and bryozoans and sponges. So these were, all of these groups of animals were instantly gone at the end of the Cretaceous. And if we look at some of those sediments around the world, here in, I think in Denmark, where have I said that one is? In New Zealand and here in North Dakota, you know, we go up, we have dinosaurs, we have sea reptiles, we have flying reptiles, and suddenly we don't. There are no more. Same with each of the sediments here. We have Triceratops living here. This is in North Dakota. Suddenly we don't. And the same in New Zealand. There's a large number of species that died out there as well. So something happened throughout the world, very catastrophic and very suddenly, as far as geology is concerned. And it was in the 1980s that a team were looking at the geochemistry of this horizon all over the Earth and found that it was very rich in an element called iridium. Let's just look at iridium here. It's here on the periodic table. It's right next to osmium. It's the densest or second densest element, depending which paper you read. It's a nice silvery metal, but it's characteristically very, very rare in the Earth's crust. The typical value is 0.02 parts per billion. It's one of the least common elements in the Earth's crust. However, in typical meteorites like carbonaceous chondrites, for instance, it's there at several orders of magnitude higher, about 500 parts per billion. So it's much more common in the solar system materials and primitive meteorites than it is in the surface of the Earth. So this led this team up here, the Alvarez, it was a father and son team, and other co-authors as well, to suggest that iridium was actually derived from an impact, a large impact on Earth. They didn't know at the time about the Chicxulub crater. The Chicxulub crater wasn't publicized until a few years later, and it was only a few years after that that they actually associated the impact of a large object, the impact of that supplied that iridium, with the Chicxulub crater. So if you look at this as a section through the sediments they were looking at in Italy, you look down here, we have almost no iridium, no iridium, no iridium. As you got to that layer, suddenly a spike in iridium, and then it dropped down again. And so this anomaly has now been associated with the impact and with that large crater. So if we look at the evidence, really, the evidence all points to, here's a gravity map of this is the coast, this is Yucatan, this is the Gulf of Mexico here, and this large rounded object. You can't actually see it on the ground, but this is a gravity map where they've been able to reveal the crater. This large crater is coincident in time with that iridium layer, with the sudden demise of the dinosaurs, and about 75% of species on Earth. One of the things that we also got with this crater was impact glass that spread up into the atmosphere and deposited all around the Earth. And this is some of the spherules that would have been called tektites, but they've been in sediments for 66 million years and have altered to clay minerals. But these were found in Haiti, just within that horizon that had that iridium layer. So how common are these impacts? And I put down a selection here, a small selection of recent impacts around the Earth, ones where we can actually identify a crater just in the last few thousand years. From Carancas, and I put this in blue because this was quite unusual, 2007. Socotra was largest crater was 26 meters in 1947. The Tunguska event, which most of you heard of from 1908, where several thousand square kilometers of trees were flattened in Siberia. Nothing's been found from that impact, so it was something that looks like it exploded in the upper atmosphere. And then one of the largest craters that we have, 116 meters in diameter, was formed in about the 1860s in the empty quarter in Saudi Arabia. So the real question is how many, this is just a small selection over the last, let's say, 1,000 years or so. So what this is really telling us is that there's been craters all over the Earth, but most of them aren't preserved. They've been in environments where there's active geology, or there's active erosion, or it's in a jungle environment. All these events, for instance, Wabar and Tunguska, most of the evidence of that is gone now. So really what we can do is to look at the size of the event and say, well, what would happen as it gets larger and larger and larger? And obviously, fortunately for us, the really large events are actually very, very rare. So the small events like A and B, so Chelyabinsk and Carancas, these are things that either have high altitude breakup, which with Chelyabinsk, or Carancas, which was that unusual one that came in at a low angle and formed a crater. That crater will be gone in a few years. It's in a low-lying floodplain. There'd be no evidence of that crater in 50 or 100 years' time. It would be completely gone. We have Tunguska-like events. Where, again, this is regional. Again, it's a few thousand square kilometers of trees. If you go there now, there's almost no evidence whatsoever that something happened just over 100 years ago. But as you get larger and larger and larger, like up to C, the C was one I was not able to talk about just for time, the Australasian tektite strewn field. This is something that happened about 700,000 years ago. Probably formed a crater about 40 kilometers in diameter. We can't find it, though. We haven't found where it is. But it's left its evidence as tektites spread over approximately 30% of the surface of the Earth in Southeast Asia. So something hit, instantly melted several thousand square kilometers of the ground and sprayed that melted material all over the Earth. But again, even though that sounds huge and dramatic, that still wasn't large enough to cause a global event. And it's only these super rare, called extinction class events, happen every 100 million years or so, that cause real global effects. So fortunately, what we're saying here is that we're safe. And there's been several studies that have begun to look at, well, what is the actual frequency? And as we said, the larger the object, the less likely it is that we're going to have a fall. And this is a recent paper from in 2013 in the journal Nature. And I've put up here equivalent diameter they put, and I put this, they had it as a cumulative number impacting, so I changed it over to numbers per year. Small things, meter-sized, hundreds a year. Things up to once a year, we'll get something up to almost 10 meters in size. Chelyabinsk, maybe every 10 years or so, or maybe, or every 10 years, or one every sort of generation or so, somewhere along here. So once a generation, we could expect to see something as big as Chelyabinsk. But something as large as Tunguska, which, again, flattened about 1,000 square kilometers of trees, only every about 10 generations or so. So again, for a local environment, for a local region, these impacts are going to have significant effects, but as the world as a whole, as the Earth as a whole, it will have almost no significant effect. So I've got two more slides. This is one that just came up in the Telegraph newspaper a few days ago, 9th of February. Asteroid will zoom past Earth in March, flyby. And what's really interesting about this, so this is actually an asteroid that passed by the Earth in 2013 when it was first observed, came within 1.3 million miles of the Earth. It's going to pass by the Earth again in a few days. And this is the prediction from the scientists. It's either going to get between 11,000 miles from the surface of the Earth to 9 million miles from the surface of the Earth. So in other words, we don't know its orbit very well. So there's huge error bounds on there. But even if it were to impact with the Earth, it's only about twice the size of Chelyabinsk. So even if it did land, it would only make probably about a 600-meter crater. And it's going to, but because we know so little about the orbit, the scientists predict that there's about a 1 in 250 million chance that it will actually impact the Earth in, what did they say, 2017. So what I really hope is that you go away with, we're safe, basically. Yes, there's going to be some relatively large impacts, and for scientists, it's fantastic. We have materials to study in the lab, and collectors as well have materials to collect as well. So the real question is, will there be another large impact? And the answer is obviously yes. But it's unlikely to be anytime soon, because if it's really large, kilometer size or larger, we would have seen it. We'd know the orbit already. Where will this next large impact be? We have no idea on Earth. And finally, when will it happen? Hopefully not soon. Anyway, I'd like to thank you all for your attention. And here's a picture of the meteorite vault upstairs. Some of you were lucky enough to see it about an hour and a half ago. Anyway, thank you. So we have time for questions. Either you can have the microphone, or you're gonna this. I'll just turn that one on. If you've got a loud voice, just project it and ask, or you can wait for the microphone. And just.
How do you know when meteorite comes to Mars or asteroid?
Well, it's basically the geochemistry and the isotopic composition. So for Mars, for instance, I mean, the telltale sign is it's got bits of trapped Martian atmosphere in it. And the Martian atmosphere in particular has a very distinctive argon-argon ratio of isotopes that say, yes, this is definitely Mars, and it's very distinct from Earth. So for the Mars, we can tell quite easily. If it's from the asteroid belt, well, there's a lot of different materials, and isotopically, again, There's a lot of ways that we can distinguish them. But a lot of the meteorites, they've got little lumps of nickel-rich iron. And those are things that we don't find in the surface of the Earth, because nickel-rich iron will rust quite quickly. Who was next? There's a question way back there.
Those future things, how many of those?
I think I would have to. It's not really my field. You would have. There's an impact database online. If anyone knows, please say. But I think the Chicxulub one was the second largest or third largest crater of that size. So there might have been more in the early history, the early evolution of the Earth, but over the last few hundred million years, not very many, fortunately. Any other questions? Why are there so many? It's impacts on Mars. So it's been modeled and impacted at the right angle, hitting the surface with a large enough body. Will actually eject material straight off the surface. It's like a shock wave that basically propels it directly up above the atmosphere. And with enough velocity above the escape velocity, will actually leave the atmosphere. And what we have on Earth, Mars has a very, very tenuous, very thin atmosphere. So a lot of things don't break up the same way they break up here on Earth. Our atmosphere, like we saw with Chelyabinsk, it protects us from a lot of these medium-sized objects.
Is there a potential initial entry angle that a large asteroid could take that would allow it to survive or mostly survive in impact on Earth?
And that's a good question. That's what we saw. I think prior to Carancas, we probably didn't think that to be the case. But Carancas was really the one that said, oh, and I don't know what the angle is. We'd have to go up and look at the paper. Let's say, it's probably, if here's the Earth, it's probably a very low angle trajectory into the atmosphere to be able to survive. So it has to be relatively low angle. But that's going to depend also on the type of material. So in this particular case, it needed a very low angle because it was such a friable material. But if it had been, for instance, an iron meteorite of a particular type that didn't break apart very easily, could have had a higher angle as well. And for the really large objects, for the things like the one that made Meteor Crater, that thing is so large, it's got so much mass, it's got so much kinetic energy that it essentially punches a hole through the atmosphere. Yes, you're going to get a spectacular fireball, but the thing is so big, it just goes straight through the atmosphere and hits the ground at nearly the same velocity as it hit the upper atmosphere with. It does, and that's what you're seeing is the meteor. So when the object comes into the atmosphere, let's say it's coming in at 20 kilometers per second, what it's doing is it's hitting the air in front of it. That air is pushing the air in front of it, so it's compressing the air in front of it. That hot air then flows over the meteor and heats it up to high temperatures within, I think, something along the lines of 8,000 degrees, almost instantaneously. And that high temperature then ablates the surface very rapidly. And so the small objects could be totally ablated, whereas the larger objects can survive the passage through the atmosphere before they either hit the ground or break up in the upper atmosphere, the lower atmosphere. Yes, so in that picture that I showed, there's approximately 3 minutes between that superheated event and then it breaks up. And now it's got 3 minutes for it to fall down. So in that, let me go back to that slide, because it's important to see what's happening there. So everything is so rapid in this first 4 seconds that the heat doesn't have time to get into the stone. And it would be a little bit like, what's that dessert, the baked Alaskan. You can put it in the oven, take it out after a while. It's only the outside that's hot. The inside is still cold. But if you were to leave it in there for another hour, everything would melt. And it's the same thing with this. It's only 4 seconds or so that it's coming through the atmosphere. And even though it's 8,000 degrees, it's only the surface that's ablating. The interior doesn't have time to heat up. So once it explodes in the stratosphere, those pieces that fall, that very thin skin that was at high temperature, it's only less than a millimeter thick, has time to cool down, but the inside is still at the same temperature as whatever it was in space. So why don't we take, what are we, another question or two? Okay. Any questions way at the back there? Well, I mean, a complete global killer would be Theia, I suppose. Theia was the hypothetical, not so hypothetical, was the object that is thought to have that hit the Earth 4.4 billion years ago that formed the moon. That would completely remelt the whole surface. It was about Mars-sized. So that would have melted the whole Earth. So that would kill everything. Oh, is that a good one to stop on? Okay, why don't we finish there?
Thank you, everyone, for attending. Thank you, VIPs. Thank you, audience members. March 17th is our next New Discoveries lecture with Hillary Hartnett, Living in a Wet Desert in Arizona Story. There's more information about our lectures and along with a flyer on how you can support CC and have more of these events for you to enjoy. Thank you. Have a good night.